In the present video, we will calculate the deformation of bar of uniform strength. A bar of uniform strength is refers to stress remains the constant throughout its length of the bar when it is subjected to axial loading. Let's consider a bar which is subjected to tensile force capital P. Here, cross-sectional area of the bar is constant. So, stress at this in this cross-sectional area, let's consider that is the sigma 1, which is equal to the P divided by capital A. Similarly, stress at this in this cross-sectional area, let's consider the sigma 2, which is also equal to the P by A. So here, stress in the bar is constant throughout its length because bar cross-sectional area and applying load both are the constant its throughout the length. But in some cases, the axial force is not the same in all the sections. For example, bar is subjected to the self weight. In the previous lecture, we discussed this kind of the example, and we know that when the stress sigma equal to the Wx divided by capital A, where Wx equal to the weight portion below the section, which is equal to the gamma Ax, where the gamma equal to the specific weight and x equal to the distance from the free end. Here, weight Wx is depends on the section of portion from the free end. So, stress is maximum at the top portion and minimum is the lower end portion of the bar. So, in this example, stress is the not same in the all the sections. To overcome this, the cross-sectional area of the bar is varied along its length so that the ratio of load to area remains the constant at every section. So we have to observe in this picture. Here, cross-sectional area of the bar is varying along its length. So this ensures that the each part of the bar carries the same stress, which making the design is economical and the safe. Bars of uniform strength are commonly used in structures where weight reduction and efficient material utilization are the important. So, in bar of uniform strength refers to stress is the constant and cross-sectional area is the variable, and these are used in the when the axial force is varying. Let's see the calculations to find the deformation of a bar of uniform strength. For a bar to have uniform strength, the stresses at any section due to external load capital P and the weight portion below it should be the constant. So let's see in this picture. Here, cross-sectional area of the bar is varying and stresses at any section is the constant, and applying the forces are the capital P, external load and weight of the portion. Let's consider an elementary section of the length delta x at a distance small x from the lower end. So here we are considering the elementary section which having the length is the dou x and which is the placing the distance is small x from the lower end. The bar is subjected to a pull capital P at the free end, and let's consider the capital A is the cross-sectional area of the free end and capital AX is the cross-sectional area of the bar at the lower end of the elementary section and AX plus dou AX is the cross-sectional area at the upper end of the elementary section. We know that for a bar of uniform section, stresses at every section is the constant. So, stresses at free end sigma equal to the stresses at lower end of the elementary section sigma x equal to the stresses at upper end of the elementary section, that is the sigma x plus dou x is the constant. So, stresses at free end, that is sigma equal to the forces on free end divided by cross-sectional area of the free end, that is the sigma equal to the P by A. Similarly, stresses at lower end of the elementary section Wx equal to the forces on lower end of the elementary section, let's consider Wx divided by cross-sectional area of the lower end of the elementary section, that is the Ax. So, sigma x equal to the Wx divided by Ax, and stresses at upper end of the elementary section sigma x plus dou x equal to the forces on upper end of the elementary section divided by cross-sectional area of the elementary section, that is the W dash x divided by Ax plus dou Ax. So, we know that when the stresses at every section is the constant. So, this equation we can be rewrite as the sigma equal to the P by A, which is equal to Wx by Ax equal to W dash x divided by Ax plus dou Ax. So, here Wx equal to the forces on lower end of the elementary section, which is equal to the external force, that is the capital P, plus weight of the bar below the section, that is, let's consider the W1. So, Wx equal to the P plus W1. Similarly, W dash x equal to the forces on upper end of the elementary section, which is equal to the P plus W1 plus weight of the elementary section, which is equal to the gamma Ax and dou Ax. So, W dash x equal to the P plus W1 plus gamma Ax into dou x. So, here let's consider the gamma is the specific weight or unit weight of the material, which is equal to the rho g. So, from the equation 1, we know that sigma equal to the P by A. So, this is we can be rewrite as P equal to the sigma A. Let's consider this is the equation A. Similarly, from the equation 1, sigma equal to the Wx divided by Ax, which is equal to the sigma Ax equal to the P plus W1. Let's consider this is the equation B. Similarly, from the equation 1, sigma equal to the W dash x divided by Ax plus dou Ax. So, this equation we can be rewrite as the sigma into Ax plus dou Ax equal to the, we know that when the W dash x equal to the P plus W1 plus gamma Ax dou x. So, sigma into Ax plus dou Ax equal to the P plus W1 plus gamma Ax dou x. Let's consider this is the equation number C. So, from the equation B and C, subtracting the equation B from the equation C. So, this is the, here we are subtracting the equation B from the equation C. Then here, so sigma Ax and sigma Ax will be cancelled. and the PW1 and PW1 is the cancel. Then sigma dou AX equal to the gamma AX dou X. So from this one we can be written as the dou AX divided by AX equal to the gamma divided by sigma into dou X. So now we have to integrating the from the both of this side. So have to integrate the dou AX divided by AX. So limits are the, so from A to AX. So integration of dAX divided by AX with the limits of the A to AX. Similarly, we have to integrate the gamma divided by sigma dx integration. So limits are the, here x value is the 0 and here x value will become the small x. So limits are the 0 to x. So integration A to AX dAX divided by AX equal to the integration of 0 to x gamma divided by sigma into dx. So from this one we can be written as, so log of base E AX divided by A equal to the gamma by sigma into x. So this equation we can be written as the AX divided by A equal to the e to the power gamma x divided by sigma. So from this one AX equal to the A into e to the power gamma x divided by sigma. So which is equal to the A into e to the power rho gx divided by the sigma. So here AX is the area of the cross section of the bar at a distance small x from the free end. Obviously area at the support, let's consider AS, which is equal to the A into e to the power gamma L divided by sigma equal to the A into e to the power rho GL divided by sigma. So this is the calculations for the deformation of the bar of uniform strength. Thank you.